Thank you very much. First of all, I want to thank you for inviting me here. This is the first time in many months that I'm giving a talk. Sorry. Qué gusto. Right. So this is the first time after many months I'm giving a talk face-to-face, so I'm very glad of that. I've subtitled my talk, Artificial Intelligence and Innovation in Hospitals, Lights and Shadows, because as you are going to see, not everything is so nice in this field. And I'm going to address some of the questions you previously raised this morning, which I think are quite important from a practical standpoint. So let me first of all ask you a question. So do you think that the many applications using artificial intelligence in medicine are really innovative? So you may say, of course, they must be innovative. This is the most innovative thing since many years ago. Well, let's see. Let's go step by step. So to answer this question, probably we should reach an agreement on the definition of artificial intelligence and a definition of innovation. Okay, so this morning I remember Jorge was talking about the definition of artificial intelligence, and you realize that this is not so easy. So in most cases, the definitions of artificial intelligence rely on saying that it is something similar to human intelligence, but in a machine. The little problem with this is that we don't know either what human intelligence is. So then this is quite a problem. Whatever it is, what's clear today is that it's everywhere. So artificial intelligence is everywhere. It's fashion. It's well-funded. That's nice too. And for instance, I make a few counts in the last Congress of MICAE, which is a congress on signal and image processing. Above 85% of the communications dealt with artificial intelligence. So every engineer in the world nowadays working in this field is using artificial intelligence, okay? Not only every engineer, so you can find artificial intelligence in irons and everywhere in the world, okay? I'm not sure to what extent this makes sense, but anyhow, this is the real thing, okay? Is that important to have a definition of artificial intelligence? Depends on who you are. Probably for us here is not so important, but if you are working in FDA or in the European Medicine Agency, the EMA, having a definition for this is quite important because the procedures you have to follow to provide the clearance of different products is different depending on whether there are artificial intelligence or not. So in this case, the EMI has spent a lot of manpower, I guess, to reach this horrible definition in which artificial intelligence is defined in only 10 lines of obscure statements. But anyhow, this is necessary, and you will see why in more detail in next slides. So, why there is such enormous boom of artificial intelligence in medicine, in particular deep learning methods? There are several reasons for this. One is that nowadays, this is much easier to do than before because we have access to very powerful machines, and even we don't need the powerful machines. We can just use cloud computing, so you just rent computing power and that's it. So this is much easier than before. On the other hand, from the software side, we have availability of many different platforms that reduce the programming effort a lot, okay? So, and this is evolving very, very quickly, so I'm sure that in a very short time, anybody at home could be able to download a certain framework and actually start programming artificial intelligence in high school, okay? That's going to happen for sure, okay? On the other hand, as you will know, some of the techniques, deep learning in particular, needs big data sets. But nowadays, because of big data in hospitals, it's becoming easier and easier to really have access to huge data sets with clinical data, okay? So, and finally, and this is important because this will represent an advantage and also a shortcoming, deep learning made a difference. With the traditional machine learning approaches, you know, what you have to do, you have data, and then what you have to do is to select or extract from those data some specific features, which are the ones which are fed to the algorithm that is going to perform the machine. So we have an expert that analyzes data and say, okay, this is important, so this is what I'm going to introduce in my algorithm, okay? However, with deep learning, we can get rid of such an expert. We no longer need to decide a priori which are the important data there. We feed everything into the deep learning algorithm, and the algorithm will decide what's going to take into consideration or not. Okay, so this makes things much, much easier, but has a few shortcomings we are going to discuss in a few slides. Okay, this makes it much easier to use. So this is about artificial intelligence. What about innovation? What's innovation? There are many definitions for this. I like this one very much because it's very short and clear. Innovation is the profitable implementation of ideas. That's innovation. So there are three keys here. Well, one, we must have some idea, obviously, a novel idea preferably. Okay, so we need novel ideas. That's not enough. We must implement those ideas, and that's not even enough. We must obtain something profitable. Profitable in this context does not mean, or does not only mean that you generate revenues, economic revenues. It may mean that you increase value in the healthcare system somehow. So you may reduce costs, you may increase the health of patients or whatever. So you generate value. Okay, if you generate value, then this is going to be innovation. Well, I don't have much time to discuss. This is quite interesting. It's the neighborhoods of innovation. You can find, for instance, you have something which is novel and it solves a problem. That's called an invention, but it's not necessarily innovative. To be innovative, it has to produce value. Okay? If you have something which is a solution that produces value, but is not so much novel, that could be called optimization. It's interesting, but it's not innovation. So for innovation to take place, you need the three things. Novel, it solves something, it's implemented, and produces value. Okay? So now, if we agree on the definitions of artificial intelligence and innovation, let's make some numbers. So I spent a few minutes working at home these days, and I entered in the Pubmed database, and I wrote artificial intelligence or machine learning or deep learning, looking for papers dealing with these things. Okay, obviously this is just an exercise, so this could be done much better. But to my surprise, I found over 100,000 results, and as you see, they are following an obvious exponential increase in the last years. Okay, so there's a huge amount of work in the academic world with publishing things about artificial intelligence. And then I made a second exercise that was entering into the FDA and looking for cleared applications in clinical use. So I entered there in something which is called artificial intelligence machine learning enabled medical devices. I scrolled down to the end of the page and I found 343 entries. This is as of it's September the past year, so it's quite modern. And obviously this is just an exercise. You should not, I mean, you should take these numbers with a grain of salt, because there may be more applications, for instance, applications who are not directly dealing with the patient, but with the decision making in the healthcare system, which probably are not here. And you may also have some applications which have managed to dodge or avoid the qualification as medical devices. That makes things easier, a bit tricky, but anyhow. So taking this just an example, if we make, one important thing here is that you may think, okay, software is not there, you're saying medical devices. No. Nowadays, if your application is going to influence somehow the course of a patient, that's going to be considered a medical device, and this is the term that has been coined, software as a medical device. Okay, so needs approval by, depending on where you are going to use it, in America or Europe, from the FDA or for the EMA. Okay, so let's divide 343 over 100K. It's around less than 4 per 1,000 of success. Okay, again, take the numbers with a grain of salt, but this means that we have a huge mismatch between the number of works which are in the academic world and the number of products we have in the clinical world. So, oh my God, we have quite a problem here. So what I'm going to try in the rest of my talk is explain what may be the reasons for this huge problem we have, okay? So why implantation of products with medical artificial intelligence is so challenging? Because they fail. They fail. Everything fails in the world. So we, as physicians, we fail. But what happens when you fail? When you are a doctor and you fail? Most of the cases, nothing happens. Because we all assume that we can fail. So if your failure took place in what is called a framework of something which is called lex artis. So lex artis means that you are using the proper methods. Then if you make a mistake, nothing happens. But what if you are an algorithm programmed by, I don't know, Philips, General Electric, or whoever else? If you're an algorithm, you will be liable for that mistake, and probably the patient may claim for a compensation that may be a huge compensation, which is something that does not happen if you are wearing a white lab coat. So this is a big difference. So that's why we are so concerned with failures with software system, and I mean, contradictorily, if you wish, we are not so concerned about failures of physical or natural doctors, okay? Let me commend you a couple of cases. This is the famous Tesla case that you probably are aware of. This is, as you see there, in the upper side of the picture, you see how the car was after the crash. And down there, you see what was the problem. This huge truck was across the road, and the car simply doesn't see that, or was unable to interpret that is a truck. So, and then because of that, we are having now so many problems with the authorization of self-driven cars, you know, okay? This is one case. This is another case, again, with cars. Probably you know that Volvo, it's a few years, implementing artificial intelligence-based aids for the driver. And one of the things they do is to recognize, with using deep learning, by the way, recognize pedestrians, different types of animals, cows, horses, dogs, etc. And then when they move the cars to Australia, they realized that the car was mistaking kangaroos, because that was something was never trained with, and the cars didn't know what was that. So they have to spend a lot of time driving cars all over Australia, looking for kangaroos, etc. Okay, so this is what happens in other worlds. What may happen in medicine, and in this particular case, with another thing which is particularly worrying or peculiar to me. It's something called adversarial attacks. How many of you have an idea of what adversarial attacks are in this area of artificial intelligence? Not many. Adversarial attacks is a malicious use of exploiting deep learning systems. And the idea is that you can somehow tailor or slightly modify the input to the system in such a way that you can induce the system to generate a wrong output, okay? And there are many there are many examples. You can find hundreds of them in just by Googling a little bit. This is very nice. So this is a system for recognizing animals. The left one is a duck. Then you add up this noise, this color noise here. You obtain the second image in the right, and now it's a horse. Okay? So what's worrying here? So what's worrying here is that probably what the deep learning algorithm is learning is not the same thing we understand as being a duck. So to us, the right picture and the left picture are obviously, both of them are ducks, because we know what is being a duck, so to speak, okay? But the deep learning system has learned something which may be, somehow stupid perhaps, and which is not the real concept of being a duck. Ducks are not so interesting for physicians, but let's see a different thing, a system to detect a melanoma. So this is a deep learning network. By the way, down there you have the publication where these things are published. So the left image is an original image, which is classified as benign by the system. Then we add up that noise that you see there, and then the image is classified with a huge confidence as malign. Okay, but it's the same image. Even worse, you just rotate the image. The left image is benign, I rotate 90 degrees, and now it's malign. Okay, so then our concern here is what the hell the deep learning network is learning. Because this is not, I mean, if we have a resident and we are teaching him or her how to interpret radiological images or whatever, we say, hey, look here, look there, take this into consideration. So we are doing this feature extraction stage. With deep learning, we have saved the money of doing such an intermediate feature extraction step, but we are paying in a different money, okay, in a different coin. So these are adversarial attacks. You can wonder to what extent anybody can be interested in cheating artificial intelligence systems. So why to do that? It seems so stupid. Okay, imagine that money is involved. When money is involved, anything stupid might happen, you know perfectly, okay? So for instance, if, and this is the case, in the US there are some insurance companies which are deciding whether to reimburse and the amount of the reimbursement of certain medical processes depending on the content of the electronic clinical record, okay? So if we can tune a little bit the electronic clinical record in such a way that we get the highest possible reimbursement, that's nice. So for instance, in this case, if we classify the patient as he or she has metabolic syndrome, heart disease, and obesity, this is reimbursement is denied. And we say benign essential hypertension, hypercholesterolemia, hyperglyceridemia, which are the key points of the metabolic syndrome. In this case, the reimbursement is approved. Okay, so this is adversarial attacks. So let me shift gears a little bit and try to see what's how can we face this kind of problems. So this is what we are doing in medicine for many years. Okay, we have a kind of set of input data that can be images, omics data, and clinical record, etc. And we want to produce one output, which is diagnosis, maybe predictions, risk factors, therapeutic suggestions, things like that. Okay, and my point here is that it doesn't matter so much what is the black box there. That black box may be the traditional one, maybe epidemiology, maybe biostatistics, or that black box may be made up of artificial intelligence in general or deep learning in particular. Doesn't matter what I have inside that black box. This whole setting, this whole framework has a common factor, which is how I'm designing the study. So if the design of the study is wrong, then I am going to get wrong results, no matter I'm using biostatistics or deep learning. Deep learning does not protect me against design flaws in the process. Okay, so somehow let me try to simplify the question and say that there are two different stages. So from the real world, we have a first stage, which is how we obtain data. And this includes sampling, this includes the epidemiological design. I'm going to talk a little bit about this in a moment. And then once we have the data, we go to the second stage, which is I will decide what is my network architecture, the hyperparameters, how to train, blah, 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 okay? And the interesting point here is that there are two different guys involved here, because in most cases, the data set has been produced by clinicians or by healthcare professionals, while the second stage is typically in charge of engineers or people like that, okay? And we are going to see why this is important. This is important because data are the key piece in this game, okay? So nowadays, I'm somehow throwing stones against my own, but it's not so difficult to find technical people able to deal with artificial intelligence. There are in many universities, in many places, amateurs, so you can find people who more or less skillfully can use artificial intelligence programs and platforms, etc. However, finding good data is extremely difficult. So data are the key component for the success of any machine learning or deep learning in particular system, okay? And this for you, that as far as I understand, are coming mostly from the healthcare sector. This means that the hospital has the data, and the hospital will be responsible for validating those results. So the hospital has the key for the whole thing, okay? And if the hospital has the key and the value is in the hospital, the next question could be what the revenues for the hospital are going to be in this kind of processes. Because up to now, as you see, in many cases, what happens is that some engineers from a company, from a university or wherever, come to the hospital and say, please, don't you have some data there to play with? And then if they produce something which is valuable, how much is the revenue I'm going to obtain? Because I produce the data, which is the key part of this thing. I'm afraid that in this talk I have a lot of questions and not so many answers. But I mean, if you are aware of the questions, we have it's not so bad. So let me very briefly, in this case, to review what kind of problems we can have with those data. I strongly recommend you to read the paper, which is down there in the slide. It's in the American Journal of Radiology. It's a paper very easy to read for non-technically skilled people, and has a very nice review of all the problems that may happen. And what I have there is just a summary of them: overfitting, p-hacking bias, confounding. We'll see what these things are and how they are related to the design of the study, and not so much to the fact of using properly the software of the platform. So, for instance, overfitting. Overfitting has been already mentioned this morning, I remember. And this is something that happens when you are, so to speak, quite ambitious with your model, because it has a lot of parameters, but you don't have enough data so as to feed such an ambitious model. Okay. So in this case, the symptom of this is that typically for the training data set you obtain very nice results, and when you move to the test data sets, the results are not so nice. Okay. If this happens, what we can do? We can, obviously, this is easy to say, include more data, but easy to say, but not so easy to implement. Or what we can do is to change the model, reduce flexibility, reduce parameters, readjust everything once and once again, test different models until at a certain moment this works. And this will move us into the next problem, which is something called p-hacking that we are going to see. So, the real way of dealing with overfitting is only one. Once you think that your product is working, what you have to do is to externally and independently verify it in a different place. If you don't do that, we can never know if you are doing overfitting or not, because there are no objective ways of measuring this. Okay, so this is overfitting. The next point is more interesting. It's something very well known in the world of biostatistics for many years, but to my surprise, most of engineers who are studying artificial intelligence have not previously studied conventional biostatistics and the problems you can face in statistics. So the p-hacking bias consists on what I mentioned before. If I try to solve my problem, if it doesn't work, it's like Groucho Marx. If this doesn't work, don't worry, because I have many more possibilities. So I will try and repeat many different attempts until at a certain moment, hey, don't touch more because this is working. Okay? So this is what in biostatistics is called data fishing or data torturing, and it's something that happens every day. So lots of publications, or even apparently solid publications you can see in the biomedical world are just not true because of this, because of data fishing and data torturing. The problem is that we are more used to what happens in biostatistics, and you can more or less get suspicion what this is happening. In this world of artificial intelligence, things are much more difficult. I mean, it's not so developed yet, so we cannot see. Again, what is the solution for this? Test it in a different place independently. Without that, we cannot never make sure that we are not doing p-hacking. One point of suspicion is that if I had to change my model many times before getting a solution, the likelihood of I'm doing p-hacking is high, okay? That's kind of a suspicion, easy to detect, okay? More things that may happen. Confounding. Confounding, again, it's to me, I've known engineers working in artificial intelligence who do not know what is confounding. So to me, it's incredible. So you must know this before going to work with PyTorch and Keras and those things in artificial intelligence. This is so necessary. So how many of you know what is confounding? Can you raise your hand? How many of you have heard? Some of the engineers. Okay, that's nice. Many people. So this may happen. I'm going to for a medical example. If we study the number of deaths in a hospital, together with whether the patients are or not receiving antibiotics, and then we detect that the more antibiotics they receive, the more they die. So you say, okay, we shouldn't use antibiotics, obviously, okay? So the problem here is that we have a confounder variable, which is having infection, and this having infection, it's creating kind of a false association between things that really don't have to do anything with each other. In case of designs prepared to use artificial intelligence, this same thing may happen. And when this is important is when the confounder is not known. If we know the confounder, we can solve it. But if we don't know that there is a confounder, then this may happen. For instance, imagine that we are doing, we are training an artificial intelligence system and to distinguish between, let's say, Alzheimer patients and controls. And we are obtaining lots of images. But most of the Alzheimer images came from Marañón, and most of control images came from Hospital de Cruces here, okay? And then my system perfectly separates who has, who's gonna have or who has Alzheimer or not. What the problem may be, that the system may have learned that my machine in Marañón is a Philips and the one here is a Siemens, and what the system has learned is to distinguish Philips from Siemens, not to distinguish Alzheimer from normality. So in this case, it's very obvious, but there may be, when you have these huge data sets, whether you have confounding or not is not so easy to detect. If you leave the decisions to the machine and you don't think, then this may easily happen and reach quite stupid solutions, okay? Okay, another which is critically important, this is critically important, is something called the selection bias or spectrum bias. For those of you who have studied a bit of epidemiology, these things should be very familiar. So selection bias means that the patients we are using are not really representative of the whole population suffering such disease, okay? So this always happens when you work with data that comes from one department or from one hospital or from one country. If we want to have representative results, we should somehow, if we were strictly speaking, we should have a sampling of the whole world, of the examples all over the world. That's impossible. So by definition, we are always making, we always have bias of selection, always. So then, to see to what extent this selection bias is hampering my product or not, the only way of doing is what? You know already? Testing it in many places. Again, it's the only solution we have. Data snooping is, you know, data snooping is what some students do in the exams, looking, I'm not sure about this question, but my mate there, so this is snooping in English. Data snooping means that somehow, if you are obtaining the training data set, the test data set, some validation data sets, and they all come from the same place, somehow you are cheating a little bit, because you are making it too easy for the algorithm. So it's necessary to include more variability in the data set you are working with, okay? And okay, I'm not going to enter into many details here. So my take-home messages regarding biases are, first of all, most of these problems do not depend on the engineer. So when you engineers start working, these problems have already happened. But you cannot say, oh, it's not my problem. It's your problem too, okay? So it's, you have to be careful about this. They depend on the data set itself. There's no clear formulas to detect or correct them. This is quite terrible. In biostatistics, it's a little bit easier. It's not it's not totally solved, but it's a little bit easier. Here it's extremely difficult, okay? The only solution, the only safe solution is to replicate in many places. And for you who are starting in this world, knowledge of traditional approaches, let's say biostatistics, epidemiology, is very advisable, okay? Then, with all this mess, what's happening in the medical community? So we know that we have these tools which are extremely powerful, but at the same time, they may be conflictive. So what's going on here? Let me briefly review some recent papers in very high impact journals. For instance, The Lancet, in medicine. These guys say here, we have a common problem in digital health. It's what constitutes an appropriate evaluation before widespread rollout of the applications. And they say, in most cases, the validation remains centered on matching learning outcomes, and the shift to the risk of digital medicine, particularly use of artificial intelligence, are concerning. So these guys are concerned about this, okay? More things. For instance, Nature, 2018. Too many developers are not taking the studies far enough. Developers are the engineers, okay? They are not applying the evidence-based approaches which are already established and respected in the medical world for everything, for drugs, for medical devices, but you go with your artificial intelligence, you say, no, it's not my case. Those guys have to pay a lot for the clinical trial. It's not my case because mine is software. No, software is a medical device and should follow exactly the same rules, okay? Or science. In science, advanced algorithms should accept standards of clinical benefit. Predictive algorithms should be subject to rigorous audits after FDA clearance. Not before the clearance, but after the clearance. In particular, when you have imagined, this is probably the worst nightmare for a regulator. You have an algorithm or machine intelligence system which is permanently improving and learning. So the day you approve it, works like this. And 1 year after, what happens? This is the nightmare of a regulator. No, so it's so powerful from the engineering point of view and so difficult to transport into real things in the world, okay? So what are some goodness criteria for an artificial intelligence system validation? So first of all, you need unbiased design. In particular, selection bias. This is very easy to detect in principle, because if all your data came from one single place, one single department, obviously that's suffering a lot from selection bias, okay? So that means that once you have finished your product, it will have been tested in many places. I was discussing in a round table, remote in that case, a few days ago, about an artificial intelligence system that was developed in one big national hospital I think that was to predict the outcome of COVID patients in the hospital, etc. And that was working nicely with those patients, and they brought the system into another hospital in Madrid. It was tested and was quite a failure and worked like crap. So, but it worked so well in the other place. So this is a clear case of selection bias, okay? Realistic sampling. In most cases also, it happens that imagine your engineers are developing an image-based application, and then from the hospital, what we do is to give you our best images, because we want to help, so we will give you the best images. But in most cases, what happens in practice is that the images we obtain are not so nice. And then if you have trained with the good images and then move to the real world with images which are not so nice, things stop working, okay, or may stop working. Prospective, I say, avoid opportunity samples. This is easy to say again. Opportunity samples mean that your data set, the data set you are working with, has been available because your father knows whoever who works, has a friend that works in the hospital. So those are opportunity data sets, okay? In principle, that's not a very good idea. So you should do something prospective. If you have envisioned an idea of a product, what you should have is try to get the proper data for your idea and not develop your idea for the data set you already have because it was easy, okay? This is an opportunity sample. Reliably label, of course, if you are using procedures that need labeling, and using more than one, you can use the training data set, the test data set, and as many validation data sets as necessary, because if you are tuning a lot and you are doing p hacking, you should use new, fresh validation data sets each time. So this is easy to say, but not so easy to put into practice, okay? And again, external replication in other sites is mandatory. What's the problem with external replication in other sites? Let's put our feet on the ground. What's the problem of replicating in many sites? Harmonization. More on the ground.
Legal issues?
Even more on the ground.
To get
the money. This is very expensive. This is extremely expensive. Okay. Then we will deal with law, etc. But if we don't have money, we don't need to deal with law, with harmonization, or with nothing. If we don't have money, we have finished. Okay. This is extremely expensive. This is called a clinical trial phase 1, 2, 3. And you know that putting into practice clinical trials for a new drug or whatever is extremely expensive. So who can do this? Only big companies. So that's why, in most cases, I remember again, this was in a different round table, when one girl actually in the audience raised the hand and said, I would be very fond of, I don't have any problem in sharing my data, provided that it's going to be used in a public environment with no profit for anybody, etc. So that seems very philanthropic, but it's not realistic at all, because from the public system, it's going to be quite impossible to reach the final stage after passing a multicentric, proper clinical trial. So the way this can work needs the cooperation, public-private cooperation, because at the end, somebody will have to put quite a lot of money here to really round off the system, okay? So perhaps we can answer my initial question now. Is the plethora of applications with artificial intelligence really innovative? So are they solving problems and generating value? Well, if you are Vanessa, for instance, they are. Because you get funds, you publish, you live on this, so it's, for you, it's innovative. But for a clinician in the hospital, so-so, it's not so innovative. So, I mean, innovation depends on the field. So, in this case, for the engineers, if you get money, funds, public funds for this, then it's innovative because you are getting value. Who's not getting value is the clinician, who's the purported user of these things, okay? So, finally, my more than conclusions are pieces of advice for you, for those who are starting in this field. And I say artificial intelligence tools will play a key role in biomedicine. I'm sure about this. It's obvious that's going to play, and not only in biomedicine, but also, as you've seen, in ironing, because in a few years you couldn't iron if you don't have an artificial intelligence-based device, okay? But the introduction is being very hard, and you know why. This is something that doesn't fit in the framework we previously had for devices and for drugs, okay? Data and validation are the bottleneck and the key piece of value in these things, okay? And data collection needs to consider epidemiological biases. Certification of these tools is yet a challenge, so there's a lot of debate, both in the FDA and the EMA. By the way, another piece of advice is you go to FDA and EMA and look for these terms of software as a device, etc., because it's quite interesting to see how this is evolving at this moment. This is not solved, it's evolving, okay? And finally, is all this important for me? And my answer is yes. This is important for you. Please go study epidemiology, check these websites of FDA and EMA, and you will be a better engineer producing better things in the field of artificial intelligence. So, thank you very much. Surely you may have questions. 39 minutes, 10 seconds. not totally accurate.
Hi, Dr. Desco. Thank you for the talk. Really, really nice. I have a question regarding what you said right now about the regulatory complexities. You said now that EA approaches are medical devices, but I guess that if they are for diagnosis, if they are for therapeutical decision taking or for the therapeutics, the regulatory measures and processes must be totally different, no? Because, for example, in the clinical practice, we are using everyday diagnostic tools that didn't go through the same pathway that the drugs that we are using for their approval. It's totally different. So I don't know how it's working right now.
No, it's not so different. What is different is that you have different levels of risk when approving one of these things. So you have things that maybe in so-called 1A level of risk, in which case, for instance, the only thing you need is that the manufacturer must have a quality system in such a way that there is a problem, you can trace back the problem, and that's it. So you don't need a previous approval by FDA or for nobody. If it's 1A, if your device is class 2B, 3, 4, then you need a previous approval, clinical trials, etc. So that depends on to what extent an error in the system may influence on the patient. So there are systems in which if there is an error, almost nothing happens. And there are systems where if you have an error, the life of patient may be at risk. So the measures you have to adopt and the approval track is totally different depending on that.
But I guess that is...
So for instance, imagine you are approving one of these applications that obtain your ECG using the phone, which are many of them, and you get quite a nice ECG. I don't know whether to believe it or not, but it's very nice. Okay, so my problem is if I have a small decrease of the ST segment and I have an ischemia, I'm going to see it because nobody has tested that. What you test is that the ECG looks very nice. Okay, perfect. But so in that case, as this is not going to be used by clinicians, and this is not going to use to make any decision, so this is a low level. Probably it's not even a medical device, but if it is a medical device, it would be 1A category, and you don't need a lot of.
What I'm saying is that many of the tools that we are using in clinical practice are helping us taking decisions. In fact, they determine many times the decisions, and sometimes
they have passed quite a strict regulatory path.
In terms of
probably you are not aware of that, but ask the manufacturers and say how much money they had to put on the table to really get the approval of such a thing. So that's why this world is, for industry, it's a difficult world because there is so much regulated, and probably you are not aware of to what extent it has been difficult for the companies to really get the approval and the clearance from FDA or whoever. I had to approve a couple of things, and I mean, it was quite a headache. What a headache.
So thank you very much for the talk. I really like it. We'll go to study epidemiology when we'll start now. So thank you. So about going for validation data set, I agree. This is something that we always should do, but sometimes we don't have such a data. But this is really a bottleneck for most of the modeling results. Coming to neuroimaging, the problem of neuroimaging, as you said, is that when you go for different institutions, I mean, the dependence of the center is so high. So how to validate in neuroimaging by using multicentric studies, I think this is a different problem. And I don't think that we really have like some kind of normative data that could pull centers together. I really think this is the solution of a problem, but at the same time it's a new problem.
Yep.
Into the.
That's why it's so interesting, and we spend our life trying to solve that problem. The classical approach to this, or one of the possible classical approaches to this, is that if you have data that's coming from different centers, what you can do is to include the center as one more factor in the statistical analysis. So this is previous to artificial intelligence. This is something you can do, depending on how you do it. It's not so obvious because, I mean, being a factor also has many assumptions depending on what it is, should be linear, should be independent, should be many things, but it's a way of approaching. I don't know to what extent using deep learning techniques you can somehow include the site or the type of the machine as kind of a variable that may change the network. So what I'm saying is, yes, you could have kind of different networks and you switch to the proper one depending on where the data are coming. But those things are not properly the deep network. So are things which are on top of the deep network. I remember Mihaela working about how to choose which is the better approach. So when you have many approaches to solve a problem, and she was talking about having kind of automatic, kind of meta artificial intelligence system, just to choose which is the best approach. So it's something like this, having meta things, it's probably one way of trying to address that. But I mean, it's just a guess at this point. So it's quite an interesting problem whose solution may bring new problems. So it's that's why this is so interesting.
Thank you very much. You talk about how important it is to validate the research output or the things you get, and that you need a lot of money to do that. So, in your opinion, where does this money should be from? From the private industry, from the government, from the university, from the research itself? How can we get that money so we can have enough data and enough research, but a good one?
That's one of the typical problems in the field of innovation, how to fund things. And there's something which is called, I don't know if you are familiar with that, the valley of the death of the project. Means that when you have research which is at early stages and you are still producing science, then you can hopefully get funds from the public administrations to fund your projects, okay? When your project is close to the end and you have a clear market and you are expecting benefits, then it's easy that private companies will fund what is needed to really reach a product. But in the middle, you have this region which is called the valley of the death, where the project is not so novel so as to get public funds, and not so mature so as to get private funds. So that's exactly a problem we have in Spain. We have calls for very scientific things, and companies in Spain, there are not so many, but anyhow, in the world there are companies that can bring something into a product if it's good enough, but in the middle we have nothing. And that's one of the challenges in this area. So, but in my opinion, in most cases, we need the whole chain. We need to start in the public world, either academic or hospitals or both, and then move to the private companies. Otherwise, it's very difficult to end up the cycle and reach a product.
Thank you very much.